Welcome to part 6 of our ANSYS Fluent tutorial series. I'm Mohammed Timori, a mechanical engineer, and in this video, we're going to talk about an essential step before running the simulation, solution initialization. Before we dive in, don't forget to like, subscribe, and hit the notification bell so you won't miss the upcoming parts of this series. On this channel, we cover the full workflow of CFD analysis using ANSYS Fluent explained simply and practically. In this part, we go to the solution initialization section from the navigation pane. Initialization is a critical step because the solver needs starting values for all the solution variables. Without a reasonable starting point, the iterative process might fail to converge or require many more iterations to reach a stable solution. There are two ways to initialize the solution. You can use standard initialization, where a single global value is assigned throughout the domain, or use compute from, where Fluent automatically calculates values based on the flow conditions at one of the boundaries. In our case, we're going to specify the values manually, and here's what we set. Gauge pressure equals 0. This is relative to the operating pressure. X, Y, Z velocities equals 0. We're assuming the fluid is at rest at the beginning. Turbulent kinetic energy equals 0.01. Turbulent dissipation rate equals 0.01. These are small initial values to allow the turbulence model to evolve during the solution. H2O equals 0. O2 equals 0.23. CO2 equals 0. These values represent the initial species mass fractions. For example, oxygen starts at 0.23, which is typical for air. Temperature equals 300 Kelvin. This is a reasonable average ambient temperature to begin with. Providing realistic values at this step is important. If the values are too far from the expected flow field, the solver might struggle and take a lot longer to converge or worse, diverge entirely. This setup prepares Fluent to start the simulation with a balanced and expected flow field, making the convergence process smoother and faster. During a simulation in ANSYS Fluent, it's possible, and sometimes very helpful, to adjust solver settings while the calculation is running. Although in many cases you can just run the full set of equations until convergence, there are situations where changing settings mid-simulation improves stability and efficiency. For example, some equations, like turbulence or energy equations, might take longer to converge or could cause instability if turned on too early. In thermal simulations, it's often a good idea to start with just the flow, momentum and continuity equations for a few iterations. This helps establish a stable velocity field. Then, once the flow is stabilized, you can activate the energy equation and other models to continue the full simulation. This strategy helps avoid numerical errors or divergence when the energy equation is sensitive to poor initial conditions. In this part of the tutorial, we demonstrate how to do this using the case modification panel. Here's what we'll do. First, we run the full set of equations, including energy and turbulence, but for a small number of iterations, just to initialize all variables. Then we temporarily disable all equations except for mass and momentum, and run a few more iterations. This lets the velocity field stabilize. Finally, we turn the full set back on, including energy, species, turbulence, etc., and run the simulation to convergence. This step-by-step adjustment of the active equations makes the simulation more stable, and often reduces the total number of iterations needed for convergence. Now let's take a closer look at what the case modification panel does under calculation activities in ANSYS Fluent. This tool allows us to change solver settings automatically during the simulation. It's especially useful when we want to improve solution stability by solving only part of the physics first, for example, starting with momentum equations only, and then gradually enabling other complex equations like energy or species. To begin, go to Calculation Activities from the navigation pane. Check the box for Automatically Initialize and Modify Case, then click Edit. In the panel that opens, switch to the Case Modification tab. By default, Fluent runs the simulation using the current solver settings, called Original Settings, for one iteration. After that, we can apply new solver settings step by step. In our case, we want to gradually activate the equations, so we increase the defined modifications to 2. This means Fluent will first run with the original settings. Then apply a first modification, e.g., disable energy. Then apply a second modification, for example, re-enable energy for the final simulation phase. This approach helps maintain numerical stability and avoids divergence, especially in simulations involving thermal effects, combustion, or multi-species flows. Let's now configure each of these modifications properly. To automate the solver control adjustments during our simulation, we use a journal file instead of manually entering commands. These journal files use TUI syntax, text user interface, which is Fluent's command line version of what you would do in the GUI. Instead of typing each modification manually, we'll use a pre-made journal file called calc_activities.ju, which handles all the necessary steps for us. You can download this file from the description of the video below. To load the file, go to File Read Journal from the main menu. In the user_files directory, select calc_activities.ju. When prompted with the dialog box asking if the journal contains read/write commands, click No. This journal file is programmed to apply 2 important solver control modifications. Modification 1 turns off all equations except the flow equations, mass and momentum, allowing the solver to stabilize the flow field over 100 iterations. Modification 2 turns all equations back on, including energy and species, and runs the full simulation for another 20 iterations. Before running this, make sure to set the number of iterations for the original settings to 20. This means Fluent will run all equations together for 20 iterations, then follow the automated sequence from the journal file. Once setup is complete, click OK and again click No when prompted. This staged approach improves stability and helps prevent divergence in complex simulations, especially in cases with thermal effects, combustion, or multiphase flow, by letting the solution start with simplified physics before progressing to the full set. Now let's continue with the explanation of this section. The modifications you've added now include TUI commands, text user interface, which are powerful scripting commands used to control every aspect of the ANSYS Fluent solver. For example, when you want to turn off the energy equation, the corresponding TUI command is /solve/set/equations energy n. Here, the n at the end stands for no, meaning the energy equation is disabled. If you wanted to enable it again, you would simply change it to /solve/set/equations energy y. This same format applies to all the other governing equations such as turbulence models, species transport, etc. TUI commands are extremely useful because they allow you to do things that are either not available in the GUI or are difficult to automate via clicking. Using journal files like the calc_activities.ju file we used earlier allows you to script the entire simulation setup, including solver control, initialization, iterations, and even result export. The journal file that we loaded already included these commands, so you didn't need to write them manually. It automatically created 2 modifications. First, it turned off all equations except the flow, momentum, equations and ran 100 iterations, useful to stabilize the velocity field. Then, it turned all equations back on, including energy and species, and ran another 20 iterations, allowing a smooth transition to full coupled solution. These steps are especially helpful in thermal or reacting flow problems, where switching on energy and species from the beginning can cause instability or divergence. By solving momentum first, you help the solver start from a physically stable velocity field. And remember, for more advanced scripting or automation, consult the ANSYS Fluent documentation. It includes a complete list of TUI commands and examples on how to use them effectively in your simulations. Let's now proceed with the next step in the simulation process, starting the calculation. After all the setup and modifications are complete, go to the navigation pane and select Run Calculation. You'll notice that the number of iterations is already set to automatic. This is because the number of iterations has been defined earlier in the case modification panel, which we configured using the journal file. Before running the simulation, it's always good practice to save your project. This ensures that none of your setup or boundary conditions are lost if something goes wrong. To save the project, go to the top menu and click File Save Project. Once saved, you can proceed to run the calculation. Now, keep in mind, the full calculation may take around 40 minutes if you are running it in serial mode, on a single CPU core. If you're short on time or don't want to wait, a fully converged model has been provided and is available for download in the description below. You can load this model and use it to continue directly with the post-processing steps, without waiting for the solver to finish. This flexibility is especially useful during tutorials, workshops, or training sessions where time is limited. We've now reached the end of this part of the tutorial. In this session, we thoroughly covered the final steps of setting up our simulation in ANSYS Fluent. We learned how to initialize the solution with appropriate values for all variables like velocity, pressure, temperature, and species concentrations. We explored how to modify solver settings during the calculation using the case modification panel, including switching equations on and off to improve stability and convergence. We used a journal file to automate those changes using TUI commands, giving us more flexibility and control. Finally, we discussed how to start the simulation and the option to use a fully converged model provided in the description if you're short on time. In the next part, we'll focus on analyzing the results of our simulation, including temperature distributions, velocity vectors, species concentration, and more. Make sure to subscribe, like, and turn on the notifications so you don't miss the upcoming session. See you in the next video.